All right, can you all see my screen?
Yep.
Okay, I'll go ahead and get started. Hello everyone. So this is Boyuan Chen from Duke University, and we're excited to share with you our newest work, called Text2Robot, Evolutionary Robotic Design from Descriptions. So this is a teamwork, as you said, and thanks for the organizer who just named every one of us. So this is a joint collaboration between my students. Ryan, Zach, and Justin are co-first authors, and Boshi as my postdoc. So let's dive in. As the organizer just mentioned, we have so many amazing achievements over the past few years on robot design, right? So this has been a dream for us actually to come up with new designs that typical humans or experts wouldn't be able to think of and automate the entire loop of the design for virtual creators to have them to be the real physical machines. So even though we have a lot of great achievements, even in the past 2 to 3 decades, there has been always a few fundamental limitations that we kind of have to overcome. One of them would be even though the first version that we see, in 2000 has the physical robot being printed out, most of robots we see actually stay in the simulation. So we wonder how we can actually consider real-world manufacturability, electronics, and all these very realistic conditions when we need to manually create this in the real world during the simulation, during the design phase. Another thing is most of these results rely on some sort of search algorithms and mostly on evolutionary algorithms or reinforcement algorithms. However, the issue with this is we always see very good results in the end, but it takes a very, very long time for us to get there. And the reason is because we typically start from some sort of random search, some random combinations, and then we gradually and slowly improve. One issue with this is that we will need to take a very long time before we can actually see something. And we also have to assume very strict primitives. For example, most of these robots you see on the screen are sort of classical examples over the years, but almost all of these robots assume some sort of basic primitives. For example, it would be bars or a linkage or cubes that we think this could be some basic functionalities, and the algorithm learn to compose them randomly and optimize over certain objectives, and eventually we have some design comes up with. However, this may actually also limit our imagination in terms of what kind of morphology of the robots that we can build. And it's also hard for us to actually specify, aesthetic appearance of the robots, or it's very hard to specify multiple objectives that we can co-optimize between what we said, the body and the brain. So even to today, this is still very challenging to have robots being designed by machines, and it is still hard for humans too. And typically, it takes several months even to have some sort of very crude prototype at the beginning. So this is a course I teach at Duke University since I joined there 2 years ago. It's called Robot Studio, and the goal is basically students starting from scratch to design a robot by drawing sketches on the paper all the way to 3D printing, manufacturing, simulation, gate optimization, reinforcement learning, and sim to real transfer. And this is the photo we took in the end of the lecture where we do a dancing and walking competition in front of the Duke Chapel. And you can see all of these students are almost the senior undergrad students who have learned mechanical engineering, electronics, and computer science for several years, and it still takes them quite a long time. Most of these robots can walk and dance a little bit, but when they get into the competition, they always break. There's always kinds of different issues, and most of robots, especially the versions that have more than less than 4 legs, always have issues to walk. But you can still see there is a very diverse profile of what the robots look like, the aesthetics of that. And some robots are better at walking in a rough terrain. Some of these are better at walking on a grassland, and some of these are better at walking in a flat terrain. So we wonder how we can actually accelerate this process. And the most important thing for us are two things. One is how do we, accelerate this ideation process so we can generate as many solutions as possible and as diverse as possible. The other thing is how do we make sure the robots work in a physical, functional machine, right? So how do we even think about robots as a classical example of electromechanical systems? How do we automate the design of general purpose electromechanical system? And it turns out this is not something that very new for us. This has been a dream for us. At least, there was a cover article from the economics about 12 years ago where we actually see 3D printers has been deployed everywhere and it has been used vastly in fast prototyping. And you can see that people talk about the third industrial revolution, where the figure literally types our dream. We want to have a human sitting in front of a computer, and it will see all kinds of general purpose electromechanical systems that comes out and for various purposes. However, after 12 years, we still don't see anything like this. We don't have anything that human would take very minimal efforts that will have the automated manufacturing design system that comes out. So our goal is to merge this gap through something as the very first step we call Text2Robot. It is a general purpose system to design quadruped walking robot that a human just need to type in a specified criteria and they just need to type in what do you want. For example, in this case, it could be simple as a quadruped walking robot resembling a bug. So it basically has 4 steps. The first step is you generate a mesh design from a text prompt. And one of the core idea is we found that leveraging the recent advancements in foundation models, which has been trained on vast amount of internet data. And one of this model is called text to mesh, where you can give a text prompt, the model will generate a 3D model of a particular design that fulfills that text prompt. However, most of these models basically are used for game asset design, which means that it is static mesh and people cannot use that as a physical functioning machine. So our algorithm on the first step is to convert this static mesh and perfect that and also decompose that so that we can figure out how do we convert this into a kinematic model of the robot. So we can decouple the model into several links that we know where are the shoulder links, where are the knee links, and where are the body. And also where we should place electronics components in there and enable to enable fast assembly, we basically pre-design these motor boxes and the power box that will fit into almost all the robots we can design. And once you have that, you're gonna consider the electronics placement from this step. So before we even evolve or design the shape of the robot, we can already say we want to design the robot, but I want to consider electronics, the real world manufacturability, can I 3D print it all along the way from this second step. And in the third step, this gets into the classical loop of the outer loop and an inner loop optimization to co-optimize the morphology and walking policy, where we have a reinforcement learning as the inner loop to train a walking policy of the robot. And then we have a outer loop policy that exchange morphology from many different robots we can generate from the first step and second step. And in fact, we can generate hundreds of different variations within a few minutes as different variations from the first and second step. And in the end, once we have a very good policy, we will be able to consider sim to real transfer during this third step. And so the real robot will be assembled within 10 minutes, and then you can easily deploy them. And almost the videos that we show are zero-shot deployment. So there's no real world training, and they can still work very well in the real world. So here's sort of a brief overview of the geometric processing. Simply, we just use cross-sectional area analysis, where we have a plane that slices a different body of components from different directions so that we can figure out where we should place the motors. And once we have to figure this out, the real-world manufacturability are also considered during the text-to-mesh process. So it takes less than a day to actually print out the robot, and eventually you just assemble everything. You don't even need screws actually to assemble everything because of the design of the modular boxes. You just snap everything in. To optimize the performance of the robot, the users can not only specify the aesthetic of the robot, you can also optimize different metrics they care. For example, what we do here is you can either optimize for a linear velocity tracking along different directions, or you can optimize for the a okay walking behavior, but you want to optimize for energy, so you want to minimize the power consumption. And you can weight different metrics based on the user design. Of course, you can add more terms on top of the reward function, as reinforcement learning is very flexible by doing this. So this is the optimization loop where you see the initial populations were proposed by these foundation models, and you can use reinforcement learning to ask the inner loop for optimization for the gates, and then the outer loop we use a evolutionary algorithm that you can see we can on the right side you can either do crossover by exchanging the links of the body, or you can mutate the body links, for example, the change of the length or the changing shape of the growing or shrinking the shape of different links. In the end, you would basically form many different variations from different species. This is what we call a species, where you can specify what kind of species you want to evolve simply from the text prompts you have initially. For example, a robot that look like a frog or a robot look like a dog. So here are some examples. By simply changing one word in the text prompts, you can generate a very diverse set of quadrupedal robots. So in here, you are seeing 30 species in the bank. And so this is one of the plot that really demonstrates the advantage of text-to-robot. So robot grammar is one of the previous state-of-the-art approaches that try to build a kinematic chain through a grammar-based parameterization. And as you see, the yellow dots are robots initialized by robot grammar. And we train this robot to a walking behavior as best as we can. And you can see this basically fulfills our expectation, right? The first random generation doesn't give us the best walking policy, so it always goes from 0 to 20 of a reward. Where the text robot, even without any optimization, so this is just having text robot generated the first round of mesh from the foundation model, it can already surpass the best robot that we can see before. So this is about 4 to 5 times better just at the beginning. So in contrast to traditional evolutionary algorithm curve that we have seen so much that basically going from a very low value and gradually bump up, the text robot actually starts from very high. So it improves pretty slow. Even at the beginning of these robots, you print it out and we have tried it in the lab, the robot still can walk pretty well. So you don't even need to optimize anything. So just having this few minutes generation and you're good to go. And one thing is the scaling law. If you just use one species, for example, you just want a robot to look like a bug or a dog or a frog, these are the yellow, gray, blue, and red curve that shows. But then if you merge all of the species together, for example, the 30 species, then you can see the top purple curve shows that the reward also, the final design robot performance also increases with the number of species increase. But remember, the only task that we do here is just changing more word and kind of using human imaginations of what prompts I can generate for the robot. And eventually you can generate a much higher performance than what you had before. So adding more species help. So this is sort of an example of even in the first round, you can see it starts pretty high as 90 reward in contrast to 0 to 20 rewards. And gradually we improve the walking policy. And in the end, you can see the robot very quickly through less than 50 generations already converged to a very good design. And then you just 3D printed in less than a day, this physical robot just walk. And based on the optimization criteria you have, either it is a bug or a frog robot. And you can do more. For example, if you design a general purpose robots without any specification, for example, you only optimize for velocity tracking, this type of robot is what you see, right? It's very high. And we also found if you optimize for energy, you will see the robot size become smaller and the body center of mass becomes lower. Also kind of fulfill our intuition in terms of how to save energy when designing robots. We go further steps. Basically, we use parallel GPU-based simulation by simulating thousands of these kind of robots policy very quickly and evolve robots of different level of terrains. And you can see that when we try to evolve robots, they can work better on very rough terrains. This robot actually generates feet shape that is not like a two-finger feet, but actually a round shape. And this is true when we observe that when the terrain becomes really rough, the original the middle and the left shape of the feet actually will stack at a corner, but a round shape will be able to bypass that particular part. With that, I'd love to thank board organizers and the panels to help with support with this competition, and we really are really grateful for this opportunity. And also would like to thank the funding agency who support this research. And I would like to answer any questions. Thank you.